Welcome again. I see lots of people like machine learning. Thank you for coming back. So this is the last session of the day, well, almost. Thank you, Stefan, for programming a session with the hard mathematics in the last slot. Not for me, you will be the one suffering, so I have to wake you up a little. No, don't worry. The math is not so hard. So today I want to go with you through the construction of a neural network. Start to finish, including optimizations, we will be looking at these numbers, handwritten digits, trying to recognize those digits. And I actually want to take you all the way through from the simplest possible model all the way to 99% accuracy on these images. So I'm not claiming that I will teach you machine learning and neural networks, all of it in 45 minutes. But what I hope is that we can go through one example together, and you will at least know how to do this one thing really well. So let's go. What is the simplest possible model we can imagine? Just 10 neurons. So we have our images, 28 by 28 pixel images. First, we take those pixels, and all of those pixels, we just flatten them as one big vector. That's what we will use as our inputs. And now, each one of those 10 neurons does the exact same thing. It computes a weighted sum of all of the pixels, adds a constant, which we call the bias. That's just an additional degree of freedom. And it feeds this sum through an activation function. That produces a result. So what kind of activation function? We'll see several today. The one thing they have in common is that they are non-linear. Here, for a classification problem, well, the scientists that studied this told us that this activation function called Softmax was a good activation function when you wanted to obtain categories. And that's what we want. We have those 10 neurons, and we picked 10 neurons because we have 10 categories, 0, 1, 2, 3, until 9. So what we are hoping here is that if in the system the weights and biases, the degrees of freedom are chosen correctly, then if you put in an 8, the 8th neuron will actually light up very strongly and tell us, I have recognized an 8. So how does this softmax work? Well, very simply, it's just an exponential. So each neuron takes the exponential of the sum it had as an input. And then once you have taken your 10 exponentials, you normalize this vector of 10 values. Which norm? Whichever you want. Pick your favorite L1, L2 Euclidean norm. Usually here we take L1, so but whatever. So what we obtain as an output is 10 values, normalized, meaning between 0 and 1, so we can interpret them as probabilities. So this neural network will be telling us, with an image in the input, what are the probabilities of this being a 0, a 1, and so on. So let us formalize this with a matrix multiplication. But first of all, let me complicate a little. This is too simple. We will do this not for one image, but I want to formalize this immediately for a batch of images. So here, in this matrix on the bottom side, I have 100 images. One image per line, all the pixels flattened in one line. And this is my weights matrix on the top. So look at the first column of weights. I start my matrix multiply, and I use this first column of weights to compute my first weighted sum for the first neuron. Then I continue the matrix multiplication, and using the second column of weights, I again compute the weighted sum of all the pixels of the first image, and so on, until I have 10 different weighted sums corresponding to my 10 neurons for the first image. I still have my biases to add, so there is one bias per neuron, it's just a constant. I add one bias to each of those weighted sums. And now if I continue my matrix multiply, I will do the same for the second image, for the third image, for the fourth image, and so on, until the 100th image. So here I have all the weighted sums for all my 100 images and the 10 neurons. I would like to represent this with a very easy formula. So x times w, that's the matrix multiply I just explicited, that works. I have a problem with the plus over there. You see, x times w is this result. That's 100 lines and 10 columns. B is just 10 values. I can't add those two together. The shapes don't match. Well, the standard solution in Python and NumPy, which is the scientific computation library in Python, is to simply redefine plus. We want to write this as a plus. Let's redefine plus. It's called a broadcasting plus. It's not a hack. It's really how plus is defined in NumPy. It's called a broadcasting plus. And the way it works is if you are trying to add two things and the sizes don't match, don't give up. Try to replicate the small thing as many times as possible to make the sizes match. And it just so happens that is exactly what we want to do. Those 10 biases, we want them added on each line, because each line represents the weighted sums for my 10 neurons, and I want the weighted sums plus bias on each line. So it actually works. I can use this formula as the central formula of a one-layer neural network, and this is how a one-layer neural network is represented. So let's go through this again. We have images and x. 100 images, one image per line. All the pixels flattened in one big 784 pixel vector. Multiplying it by the weights matrix computes all the weighted sums for my 10 neurons and my 100 images. I add the biases, and then I use the Softmax function. I apply the Softmax function line by line. So line by line, I elevate my weighted sums to the exponential and normalize this vector of 10 elements. Next line, I take the exponential of what I have and normalize these 10 elements. In the outputs, I obtain for each image 10 values, which are the probabilities of this image being a 1, a 0, a 9, and so on. Those are my predictions. So let's see how this is written in TensorFlow. I hope this is not too surprising. TensorFlow is it's a Python library. It has this useful NN library, which stands for neural networks. It has all kinds of neural network-related functions, such as Softmax, and apart from that, it does basically matrix multiplications. So we have predictions. And now, well, this will work if the weights and biases in the system are good. What does it mean, good? Well, good means giving us good predictions. How do we know the predictions are good? Well, we will train the system for the predictions to be good. Actually, what training means is that we will be giving known data, known images to this system. It will be telling us what it thinks this image is, and we will be telling it what it should think. That is training. So we need a measure of how good the training is at one given point, and that's fairly easy to calculate. Our model is giving us 10 numbers, the 10 outputs of the 10 neurons, which are probabilities of one of the input image being something. During training, we use known images, so we know what this image is. We simply encode the known information. It's called one-hot encoding. Very simple encoding. To encode a 6, you take 10 values, all zeros, but you have a 1 in the 6th position. In that format, it's very similar. We can now compute a distance between those two vectors. And again, any distance here will work. You like the Euclidean distance, the sum of square differences, that's fine. Be happy with it. But the scientific community has a consensus that for classification problems, this distance is slightly better. So this distance, called the cross entropy, how does it work? Well, element-wise, you will be multiplying the elements of the top vector by the logarithm of the bottom vector, element by element, and then you sum all of this across the vector. You add a minus sign, obviously, because all of those values are less than 1, so logarithm of that is negative. You add a minus value. And you have a distance between what the neural network thinks and what you know to be true. Now the training is simply to minimize this distance. So let's go. Let's try to train a neural network. Let's see how this works. So here I run it. On the top, I have my training images. Those are my 100 training images I send in each training iteration. On a white background, I put them on a white background when they are already correctly recognized. On a red background if the system still misses them. So that's what I use for training. Now, to assess the quality of the training, you can't do that on the training images. Okay, you need to do that on a set of images that the system has never seen before. So I have also 10,000 test images here. You only see in the right bottom corner, you only see 1,000 of them. So you have to imagine that there are 9 more screens of test images down there. But again, thankfully, all the badly recognized ones are sorted on the top on a red background. So you see with the scale here that this extremely simplistic model, just 10 neurons, trained across 2,000 iterations, is already recognizing 92% of my test images. That's not so bad for such a simple model. On the top middle there, I have my loss function, the cross entropy, okay, computed both on the training images and on the test images. Well, it's going down. That was my goal. I was minimizing the cross entropy. I'll tell you in a second how, of course. But here I just see it's going down. And what I call accuracy, that is simply the percentage of correctly recognized images. So that one is going up. Good. It seems the training seems to be doing something useful. And those last 2 diagrams are all the weights and all the biases, so all the degrees of freedom of my system. What you see here are percentiles. So percentiles are kind of hard to understand, but basically the full extent of the colored region is where 100% of the weights or all the biases are. So basically what you see is that the weights, they started at all 0, and they evolved, and now they are between -1 and 1. The biases started at 0, evolved, and are somewhere between -2 and 2. That's just useful to see that the weights and biases are changing, which is the goal of the training, to find the good weights and biases. And you can keep an eye on this to make sure that they are not shooting in the hundreds or thousands, which would mean that your system is not converging. So this is how training works. You throw known images and known labels at the system. It tells you what it thinks this number is. You tell it what it should think. You compute a distance between those two, and use that distance to modify the weights and biases in a direction that makes this distance smaller. So let's now write this in TensorFlow. To start, in TensorFlow, you need placeholders and variables. A variable is any degree of freedom of the system, so anything you want TensorFlow to determine for you. In our case, it's our weights and biases. We will start with them initialized as 0 here, slightly later as small random values, and we ask the training to determine them for us. For that, we need training data. So for all the data that we will be inputting during training, we need, in TensorFlow, a placeholder. Here I'm defining a placeholder for x, which are my input images. Let's look at the shape of this placeholder. It's non-28-28-1. So first of all, it's a tensor. A tensor is a multidimensional matrix. That's why it has dimensions across, 4 dimensions. And none will be the number of images in this training batch, not known right now. I will provide a certain number of images during training. I don't know yet what it is. 28 by 28, that's the size of my images in pixels. and 1, that was not necessary here, but this is the number of values per pixel. It would be 3 if I was handling color images. But I'm handling black and white images. I just put it there to show you where the 3 would be for color images. So placeholders, variables. Now I have everything to write my model. So look at the first line. You should recognize it. That is the one-liner representation of one layer of a neural network. Well, we have a neural network with just one layer, so that's all there is to our model, just that one line. What you don't recognize is this reshape operation. That's simply because our images were 28 by 28 pixel images, and I told you we need them as one big vector, all the pixels flattened. So that is what reshape does. And the -1 in the shape simply means there is only one solution figured out. So if you skip the reshape, what we have is a matrix multiply between x, the images, w, the weights, plus the bias, fed through the softmax activation function. That's exactly the one-liner we have seen before. So this produces the predictions from our model. I define a second placeholder for the known labels for my images. During training, I know my images are a 1, a 2, a 3, and so on. So I need to input that information as well, and I'm ready to compute my loss function, the cross entropy. What is it? It's an element-wise multiply. The star is element-wise between my known labels and my predictions. Summed across the vector, reduced sum does a sum across the vector. And everything on the bottom, the 3 lines on the bottom, that is just the computation. I'll skip that. That is just the computation of the percentage of correctly recognized images which I need for display to put it on the curves. All right, now we are ready to train. And this is where TensorFlow really brings you a ton of added value. You take your loss function, you pick an optimizer. Here I chose the gradient descent optimizer. That is the simplest one. In the library there is a whole series of them. And you ask this optimizer to minimize your loss function, your cross entropy. So let's see this cross entropy. What does it depend on? You see the cross entropy depends, of course, on the known labels and images, so the training data. But it also depends, through the model, on W and B, the weights and biases of the system. That's exactly what we want to modify. So what this is going to do is TensorFlow here will compute the partial derivatives of this loss function relatively to all the weights and all the biases in the system. First of all, thank you, TensorFlow, for doing this for us. How many weights and biases do we have? Do you remember? Here, W variable of shape 784 by 10, so almost 8,000. So this vector of partial derivatives is a vector of approximately 8,000 different values. Thank you, TensorFlow, for computing this for us. Secondly, I would like to point out what TensorFlow does here is a formal derivation. It's not a numerical derivation, it's actually a formal derivation, which is kind of neat. And this vector, so mathematically, it's known as the gradient. And the gradient is a vector, an arrow. Who knows where does the gradient point? Yes? Exactly. Almost exactly. The gradient points up. We add a minus sign because we want to go down, and we have an arrow that goes down. Suddenly we know where down is. Let's remember, in which space are we? We are in the space of all the weights and all the biases. So if we take a step in this space, it means we are modifying our weights and biases. We want to modify them so that the error function becomes smaller. Well, fantastic. We just computed an arrow that shows us in which direction this loss function will be smaller. So that is the training loop. In the training, you compute one gradient on one batch of images and known labels. you add this, you use this gradient to modify the weights and biases, and suddenly you're closer to where you want to be in terms of loss. And you start again. Last thing, the learning rate. So if I was adding a full gradient to my weights and biases at each iteration, I would be going in the right direction, but I would never arrive. Why? Imagine you're in the mountains, you're on a mountaintop, you have a gradient for gravity, we have sensors for that, you know where down is, and you want to reach the bottom of the valley. Imagine also you have 7-league boots, and you make 7-league strides. You would be jumping from one side of the valley to the other. You would never get to the bottom. So to actually get to the bottom of the valley by following the gradient, you have to go slow. So that's what we do. We compute this gradient, multiply it by this very small number called the learning rate. That gives us small deltas to be added to our weights and biases. We modify our weights and biases and restart on the next batch of training images and labels. Here is the training loop. Before we dive into this, I have one more thing to tell you about TensorFlow. TensorFlow has a deferred execution model. So all the tf.somethings that we've been running until now, they just build an execution graph in memory. They don't actually produce values. That's useful because we want to do this formal derivation, so we need the graph for that. It's a very useful thing for distribution as well. To actually compute values in TensorFlow, you have to define a session and then do a session.run on some node of your previously defined computation graph. And when you do that, you also have to provide all the data for which you defined placeholders, because now you need it. So the syntax for that is this feed dictionary. And if you look at the feed dictionary, how it is defined, feed dictionary equals train data equals blah, blah, blah. And in this dictionary, the keys x and y underscore are exactly what you defined previously as placeholders. So this is the syntax for feeding your placeholders. And basically, what we do here in this training loop is that we use a utility to load the next batch of 100 images, training and training labels, and we run a training step. What is a training step? That's what we got here when we asked our optimizer to minimize our cross entropy. So this training step is what actually computes the gradient, applies a fraction of the gradient to modify the weights and biases. So this is how the weights and biases actually evolve during training. And you loop on this. All the stuff on the bottom, forget it. That's just for display. So I'm computing the accuracy and cross entropy on my training data, on my test data, so that I can put it on this nice little graph as the blue and red curves. Not useful for training at all. This is just to follow on my graph. And we're done. This is the full code. So let's recap placeholders and variables. Variables for all the degrees of freedom of your system, the weights and the biases, placeholders for the training data. Then you define your model, in our case just a one-liner, which gives you predictions. You load the known labels. You can now compute a distance between those two. The distance is called the cross entropy. Last two lines, simply the computation of the percentage of correctly recognized images. And then the core of what TensorFlow does, you pick an optimizer and you ask this optimizer to minimize your loss function. That gives you a training step, and this training step is what you execute in a training loop. So in the training loop, you load 100 images and labels, execute the training step, and iterate again. That's all there is to training a neural network. So, using this very simple 10-neuron neural network, and using some of these ingredients in our recipe, we obtained an accuracy of 92%. 92% correctly recognized images. Who thinks this is good? Who thinks this is bad? Yeah, this is good awful. Come on. Imagine you're the post office. You want to use this on zip code recognition. It misses 8 numbers out of every batch of 100. It's unusable. We have to do better than this. And since deep learning is all the rage, let's go deep. Actually, it's very easy to go deep with neural networks. You just have to stack layers. Look, the first layer, each neuron does a weighted sum of all the pixels of the image. Well, if you stack a second layer, on the second layer, each neuron will be doing a weighted sum of all the outputs of the previous layer. Very easy. You can stack them. The only little wrinkle is that I'm keeping my softmax activation function on the last layer because it's useful, produces nicely normalized probabilities. That's what I want. In the intermediate layers, the usual activation function is this one. It's called the sigmoid. It's simply a function that is nonlinear. That's very, very important. But simply goes continuously from 0 to 1. So let's try with this. And actually, so how do we do this in TensorFlow? This time, you will need a weights matrix and a bias vector per layer. Okay, so instead of having 1 pair, I have 5 pairs. It's also good practice to initialize them to at least the weights to small random values. Otherwise, the risk is that your system never even starts converging. So here, truncated normal is just a complicated way of saying random. So I have one weights matrix, and yeah, if someone volunteers to explain what a normal distribution is and how you truncate it, for me that's random. Now, so I have one weights matrix and one bias vector per layer, and this is what my model becomes. So you recognize the first line. We've seen that before. It's just that we are using the sigmoid as the activation function now. And yes, exactly, I see a gentleman doing this. Yes, we pipe the output of the first line as the input on the second line, and the output of the second line as the input of the third line, and so on. That's how you chain them. Until the last line, which the only difference is this last line, which has only 10 neurons, because we still have only 10 categories to recognize, uses this softmax activation function to produce probabilities. That is all that I have changed in my model. So let's run it. Before we run it, I have to confess, I lied to you. The sigmoid is not anymore the most popular activation function. Actually, it has many problems, especially if you add many, many, many layers. Here you could see it with just 5 layers. You could train with the sigmoid function, and you could see that, at least in the initial few iterations, the accuracy goes up, but not very fast. But if you add a lot more layers, you will start having real troubles with the sigmoid. So a new activation function was invented. Actually, it's even simpler. I don't understand how this works. It's just 0 for all negative values and identity for all positive values. You use this instead of the sigmoid, and suddenly you can build deep neural networks. Why? Honest answer, mathematical answer. Honest answer, nobody knows. We tried it, it works. Yeah, success. That's the honest answer, I'm sorry. Slightly more mathematical answer, well, you see the sigmoid function is kind of flat on both sides. So if you end up on those sides, there the gradient is tending towards 0. Use the gradient to go forward, so it's a problem if your gradient is getting too low, is having very low values. The ReLU function, at least on one side, it doesn't have this problem, so that's why it solves it. That was super mathematical. But actually, I'm being honest when I'm telling you that if you find a math paper explaining why this works better, it is an after-the-fact justification. People first tried it, it worked better, and then that's it. And actually, the reason they tried this comes from biology. people used to think, biologists used to think, that the neurons we have in our head, they were using the sigmoid activation function. And actually, now the consensus is more like this. They think that a biological neuron, when it receives stimulations on its axons, it produces nothing until a threshold, and after the threshold, it produces an activation that is proportional to the amount of inputs, which is a lot more like this, rather than the sigmoid function. But well, so the inspiration was biological, but then people just tried it, works better. That's fantastic. And actually, if we simply replace our sigmoids with a ReLUs, we get a much faster start. This is only 300 iterations, so just the start, it starts faster. Okay, we're happy. Let's push this to 10,000 iterations. First of all, 98% accuracy. We are suddenly, by adding a few more layers, recognizing 98% of our images. This is huge. We jumped from 92 to 98. But, I mean, those curves are kind of messy. You see all, all this noise. And look at the accuracy computed on test data. It's jumping up and down by a full %. This doesn't work. This actually means that you're going too fast. You're jumping from one side of the valley to the other. You're not reaching the bottom. So you have to slow down. But the clever way to slow down is not just to use a lower learning rate, because that would slow you down completely and multiply your training time by as much. The clever thing is to start fast and decay the learning rate to end slow. Okay, that sounds really as a very... Yep. That sounds really, really simplistic, but actually, the result of that little change is spectacular. This is what we had with a fixed learning rate of this, 0.003. By starting at that level and during training decaying the learning rate exponentially towards 0.0001, look at this. All the noise is gone. It's spectacular. All the noise is gone. Now suddenly, the accuracy, the test accuracy, is stable above 98%. It's not jumping up and down anymore. It's stable. And look at the training accuracy. The blue curve there. Across the last 2,000 iteration, it's stuck at 100%. So here, for the first time, we built a neural network that can recognize our training images with 100% accuracy. It can recognize all of them. I'm not saying that it has 100% accuracy on test images, but at least on the training ones, for the first time, it got them all correct. So we're quite happy with that. But now let's look at the loss curves. First of all, the blue one, the training loss. Well, that's what we are minimizing, so it goes down. Nice, we like that. It works. Then, but actually, we don't care about the training loss. We want to recognize real-world handwritten images. We don't care about the training data. The only thing we care about is the test loss, is how well this is performing on test data, which the system has never seen during training. And look, the test loss, initially, the red curve on the right, initially it goes down, and then there is a disconnect. So this disconnect is to be expected, okay? Because we are working only on the training loss. All the optimization algorithm is minimizing the training loss on training data. The minimization algorithm never sees the test data. So it is kind of expected that initially both of those losses will come down, but at one point there will be a disconnect because we are only working on the training data. And that has a positive effect on the test performance as well until a certain point. But what is worrying here is that this gap actually increases. When you see this on curves, you look up this in a neural network manual, they tell you this is overfitting, you need regularization, the good regularization function. I love this one, is called Dropout, and it involves shooting the badly behaving neurons. That's some methodology. So let's see how this works. Actually, you do shoot your neurons. During training, you pick a probability. Here, p keep equals 75%, which is, at each iteration, the probability of keeping a neuron in play. Which means that at each iteration of your training loop, you roll the dice and you shoot 25% of your neurons. When I say shoot, I mean you physically remove them from the system. Their weights and biases will not be updated. On the next iteration, you put them back, roll the dice again, and shoot another 25% of your neurons. That is how dropout works. Now, of course, when you evaluate, when you test this neural network, you don't test with a half brain-dead network. You put all the neurons back, okay? So you need to set p-keep at 1, probability 1 of keeping the neurons to have this during testing. I put there the code that you use in TensorFlow to implement this. Actually, the dropout function is simply something you call after your activation function. And all it does is, in this yf vector, so the outputs of the previous layer, it will replace 25% of the values by zeros. And also boost the remaining values by a compensatory factor to make sure the average stays the same. That would shift the activations otherwise, but that's a technical detail. Basically, it zeroes out 25% of your outputs. Now, what is the consequence? I mean, this is brutal. Does this really work? So let's try. But we will recap all the things that we have done so far. Initially, we had our 5-layer neural network using sigmoids. We train it for 10,000 iterations. This is what we get, 97.9% accuracy. We replaced the sigmoids with ReLUs. Suddenly, it trains faster, and we actually gained a couple of tenths of a percent of accuracy by just doing that. Still, very noisy curves. So let's decay our learning rate. That cleans up those curves. Nice. Stable, we are stable above 98% recognition accuracy, and for the first time we are recognizing all of our test data perfectly. But we have this disconnect between the loss curves. So let us add dropout. First of all, some noise creeps back. That is unsurprising given how brutal this technique is. You see how it works? You're shooting your neurons, so some noise is expected. Then look at the test loss curve, so the red curve on the right. Well, yeah, it has been brought under control somewhat. There is still a disconnect between the two test curves, but it's not growing anymore. So dropout worked. Did it help with accuracy? Well, first of all, what I find amazing is that it didn't destroy accuracy. The accuracy stayed constant here. But in this case, you can't win every time. It didn't help with the accuracy. I'm kind of stuck at 98% accuracy. I don't seem to be able to do anything, and I tried a lot of tricks here to get beyond that. So we have to revisit this concept of overfitting. Let's ask the experts. What do they have to say about overfitting? So fundamentally, what overfitting is when you give too many degrees of freedom to a neural network, too many neurons. You imagine that you give to a neural network so many neurons that in the weights and biases of those neurons, it can actually store in some way all the training data. It will create some kind of internal category for each example of a one that you have given him instead of the one as a concept. That would work for training data, but that would be terrible in real-world recognition because it will basically learn by heart to recognize the 10,000 different ones that you have in your training data set and would still be completely unable to recognize a one that I just draw now. So the takeaway here is that a neural network, you have to constrain it. You have to constrain its degrees of freedom to force it to generalize from the training data to your real-world test data. The opposite of that is if you don't have enough data. Even if your network is constrained, it has a reasonable amount of neurons. If you have only a little data, you can still store all of that somewhere in the weights and biases. You'll get the same problem. So anything you do with neural networks, you need tons of data. And then, if we did everything right here, like here, why is the world so unfair? We actually, I mean, we have a 5-layer network. I promise you, I tried to remove layers, doesn't help. So I'm still stuck at 98%. I have tons of data, so I'm not overfitting because I have too many neurons. I have tons of data. This data set has 60,000 handwritten digits for training and 10,000 for testing. So that is not the problem. I tried the mathematical tricks like adding regularization. It helped somewhat, but I'm still stuck at 98%. So the last conclusion is that for some reason, the neural network we are using is actually not capable of extracting more information from this data set. Does anyone know why? We did something pretty stupid at the beginning. Like really stupid. Any idea? Exactly, yes. We had a nice image, 2D with shapes, and handwritten digits. It's just shapes like curves and pictures, curves and circles and straight lines and all of that. And we took all of that and destroyed the 2D information. We just flattened all the pixels in one big vector. Well, it's no wonder that this system doesn't know how to retrieve this information. It's hard. So we have to build another neural network, this time designed to take advantage of the 2D information in images. And this is a convolutional network. This is how it works. So I'm going back to the generic case of a color image. So that's why I have 3 channels of information per pixel, red, green, blue. And this time, a neuron will still be doing a weighted sum, but only a weighted sum of a little patch of pixels above him. Here, 4 by 4 pixels. He does a weighted sum of just that. And then I shift 1 pixel to the right. And here, again, I do a weighted sum of the 4 by 4 pixels right above me. And second big difference, I'm reusing the same weights. Okay, so those 2 weighted sums have been computed using the same weights. Previously, in dense networks, each neuron had its own weights. Here, we are reusing the same weights. Basically, we are scanning this image. We'll do this in both directions with a little patch of weights. So if we scan it in both directions, and of course with some proper padding on the sides, we are going to obtain as many output values as we had pixels in this initial image. And for that, how many weights do we need? Well, as many weights as elements in that highlighted cube, so that's 4 by 4 by 3, which is 48, if I'm not mistaken. So 48 weights in the system. How many did we have in our simplest 10 neural network? Something like 8,000. And here, 48, that's not going to work. Not enough degrees of freedom. We need more. And it's very simple to add more. Well, let's do this again. We take a second set of weights and rescan the whole image using this second set of weights, which produces another, here, let's call it the channel of output values. And we can do this as many times as we want. And since we are using tensors, we can now write those 2 weights matrices as 1 by adding a dimension, and we have the shape of a weights tensor for a convolutional layer of a neural network. So let's go through this again. 4 by 4 in this shape is the size of the patch. We're using patches of 4 by 4 pixels. 3 is the number of channels in the input. So here we had a color image, so that's 3 values per pixel. And we did this twice, applying 2 patches of weights, which means we obtained the output twice. Let's call this 2 channels of output values. That is the last value in the shape of this matrix. Now, the last problem we face is that, well, written like this, with a number of input channels and output channels, you see what's coming. We will be able to stack them. But we still have one problem. We need to distill the information down. At the very end, we still want 10 neurons for our 10 categories. So the traditional way of doing this was to sample those answers from those patches. This is important to understand because it gives you an idea of what's going on, even if it's not what we're doing anymore. But what was done is that in the output values, you would take squares of 2 by 2 values and simply retain the biggest one. And that's what you pass to the lower layers. What's the justification for that? Well, during training, those weights will evolve into some kind of, shape recognizers. Some of those patches of weights will become very sensitive to little circles. Some of them will become very sensitive to oblique lines. So an output of one of those patches is actually something saying, well, I've seen a circle right here with a good intensity. So the downsampling, which is to say on 4 by 4 pixels, I take only the 4 by 4 output values, I take only the one that is maximal. That's actually saying, well, here I've seen something, so I will be keeping this. Here I've seen nothing, here I've seen nothing, here I've seen nothing, so I'll be dropping those. Downsampling. But actually, there is another way of simply condensing the information, that is to play with the stride of this convolution. If I am applying my patches, not pixel by pixel, but every 2 pixels, well, mechanically, I will obtain twice less values in both directions in the outputs. And that's also a way of condensing the information. So actually, today, if you see convolutional layers, you will mostly see them with only convolutional layers and no subsampling layers. I'm not saying it works better, it's just simpler to explain. So this is the convolutional network that I want to build with you. It starts with the image, going back to a grayscale image, and a first convolutional layer. So let's look at W1, the weights. 5 by 5 is the size of the patches. 1 means it's reading in 1 channel of information because we have a grayscale image. It's only 1 channel of information. 4, the last number, is because we are applying 4 of those patches, producing the output 4 times. Let's call this 4 channels of information. Now we go to the next layer, W2. Now we use 4 by 4 patches, reading in 4 channels of information because we produced 4 channels previously. And this time, we use 8 of those patches, producing 8 channels of information. Stride 2. So this time, those planes of results, instead of being 28 by 28, they are only 14 by 14, because when we do the scanning, we jump 2 by 2 pixels in both directions. And that is how we condense our information. Third layer, patches of 4 by 4, the first 2 numbers, reading in 8 channels of information, because that is what we produced in the previous layer. And we do this 12 times, again, a stride of 2. So now our planes of results are only 7 by 7, going down from 14 by 14 to 7 by 7. And now we apply a fully connected layer. So a fully connected layer is what we have seen in the first part. In a fully connected layer, one neuron does a weighted sum of all the values in this cube of 7 by 7 by 12 values. And the next neuron, right next to it, will be doing a weighted sum of all those values using its own weights. This time, no sharing of weights, because it's a fully connected layer. Last layer, our 10 neurons using Softmax as an activation function to produce our predictions. So let's see how to write this in TensorFlow. Again, you need 1 weights matrix and 1 bias vector per layer. The only difference is that for the convolutional layers, the shapes of those weights matrices are slightly different. It's what we have seen. They have this shape. And once you have that, you can rewrite your model. So this is what my model becomes. TensorFlow has this useful conv2d function, which actually does simply the double loop on the image. So you give it the image, you give it the weights, it will do the double loop. Don't mind the slightly complex syntax for strides. To be honest, I don't know why they are 4 numbers. I just highlighted in red the numbers that need to be 1 or 2 to get a stride of 1 or 2. I will read the documentation next time I do this talk to explain the other values. So now I have, and of course, once I have done this, I feed the result through my activation function, which is the ReLU. So I have my 3 convolutional layers. Then I need to reshape the outputs to get into my fully connected layer. You see my cube of 7 by 7 by 12 values. I need to put it in one linear vector. That is what reshape does. And then I add 2 normal layers. I hope that by this time you recognize these formulas. One fully connected one using ReLU, and another one using Softmax, this time with only 10 neurons in it. That's all I changed. The model and the W, the weights and biases, the definition of the weights and biases. Let's run this. And I hope that, I promised you we were going to beat 99% accuracy together. So let's see if we get there. Let's go. So it's slightly slower because, we are asking the system to do a lot more computations. But you see, even at only 100 iterations, the accuracy is shooting up pretty strongly. Actually, let me zoom because we can't see anything here. Let's go. Well, I'm already at 96%. I'll zoom more. I think I will be getting to 98 pretty soon. 97, 98, and so on. This is going to take maybe slightly longer than you have patience for, so I prepared a video for you, which is slightly faster. Let's go shooting up. I'll zoom. Oh, the 99 is not far away. We're getting there. We're getting there. We're getting there. Come on. We're getting there. In the end, we didn't get there. 98.9. Damn it. All right. We have to go above 99. So actually, I'm going to give you a trick, which is kind of a methodology for designing the ideal neural network for a given problem. First, you start by restraining your neural network a little bit until it hurts. Here, I know I can do better than this. So I know that I have not given it enough degrees of freedom. Once you are there, you give it a little bit more degrees of freedom, and you add a regularization to make sure that those additional degrees of freedom do not result in overfitting. So that's what we will do here. Look, I take slightly bigger patches, 6 by 6 in the first layer instead of 5 by 5, but more importantly, I use a lot more of them. Instead of 4, 8, and 12 patches in each layer, respectively, now I use 6, 12, and 24. More degrees of freedom, and to make sure I'm not overfitting, I add a dropout in the fully connected layer. So why not in the others? My feeling is that we don't have enough degrees of freedom in these convolutional layers, not enough neurons to start shooting them. The fully connected layer is where most of the neurons are, so their dropout will work. All right, let's try this. And actually this time, the accuracy is shooting up pretty fast. I will have to zoom to see something. Let's zoom. 99% is not far, and we are above. Yes. Thank you. Actually, we got to 99.3% accuracy. And if you go to the MNIST website, where, by the way, you will find 20 years of R&D and papers on this problem. Yes, some people had a lot of fun with this problem. The maximum they get today is 99.7%. So here, all of us together in a 1-hour session, we got not so far from what the maximum is. And to finish, I just want to show you what Dropout did. You remember last time we applied Dropout, we were a bit disappointed. Here is what we had with this bigger network, but no dropout. Just a bigger network, we already shoot above 99% accuracy, so we like that. But we have this wild disconnect between the test and training losses. So let's add dropout. On the fully connected layer, you see the test loss is very, very nicely brought under control. And just with this one little, shooting trick, we won 0.2% of accuracy, which is huge. We're fighting for the last percent here. So getting two, there are only 10 steps to go, and we did 2 of them just by adding dropout. Here it works really, really nicely. All right, so here you have the Cliffs Notes for the entire session. And I hope you enjoyed this journey through the building of a neural network. I've tried to show you how we proceed, what we follow on the curves, which solutions we apply. And also, we've seen today together 2 very important neural network architectures, which are fully connected networks and convolutional networks. If you want to follow up and have the full picture, the one you're really missing are recurrent networks. I actually did a session on recurrent networks in a university session on Tuesday. There is a video for it. You have this presentation as a link. You have my Twitter handle in case you want to say something. And so this was all about TensorFlow. We also have a managed service called CloudML for running your TensorFlow graphs in a distributed environment. So if you don't have a cluster of 10 machines under your desk, you can do your training and your serving as well, by the way, on CloudML. And if you don't want to train your own models, we actually have a couple of pre-trained models. We have plenty of data to train them on, so you can try those. There is the Cloud Vision API, the Speech Recognition API, the Natural Language Processing API, and Google Translate. Thank you. And we have 2 minutes for questions, if there are any. Questions? Yes.
Currently, that seems like much of these parameters, like patch size and
the number of neurons.
activation function, they're kind of like experimental parameters. So would it make sense to use yet another neural framework to train those parameters for the optimal value?
So the question was, we have used plenty of hyperparameters, so like the activation functions, the number of neurons in a layer. Would it be possible to train a neural network to come up with those numbers? Actually, we just released a paper doing something even better. You see those, the full shape of a neural network. What is it? Convolutional numbers, convolutional numbers, convolutional numbers, fully connected numbers, fully connected numbers. That's a sequence of symbols. So we wrote a neural network that, for a given problem description, generates a sequence of symbols that actually represent a neural network architecture, a succession of layers of this shape, that shape, and so on, that solves this problem in an ideal way. So I don't know if this will put all the neural scientists out of business immediately. They have already put all the statisticians out of business. But I think it's a very interesting approach. Realistically speaking, this is hardcore research. Realistically speaking, hyperparameter tuning is something you do yourself, with the knowledge of the system. You can do like an exhaustive search of these parameters. It's actually something you can do on CloudML. You can say, please try to fit the best values for all these parameters. It will do a grid search. The only problem with a grid search is that, these big networks, sometimes they already take a day or 2 to train. So that plus a grid search. Well, you can throw lots of machines on it, and that's what CloudML does. Exactly. Other question? Yes? The ReLU function, the question was, the ReLU function isn't a smooth function, how do you do the gradients? Ooh, your math teacher wouldn't be happy. Smooth, what's that? You have continuous and you have differentiable. What we need is differentiable. It's differentiable everywhere but in one point. What is one point in a computer? It doesn't exist. One point is has no physical existence. So in practical terms, this function is differentiable. That's all we need. All that we need is that the derivative of this function is defined. We can have a value for every point. That's the only thing we need. Yeah. But I don't think so. We are talking here. The function itself is continuous. Okay, it's not jumping. The function itself, the ReLU, is continuous. There is no jump. The jump is in the derivative of this function. So when you compute the gradient, well, yes, this gradient might have very different values for close-by values of the input parameters, but that doesn't matter. The only thing that matters is that this gradient has a defined values. You can compute what it is. And when you compute this across 100 images, which is here, it's called stochastic gradient descent. That's what we use. That's why we use mini-batching. Well, those differences of opinion between the gradients in close-by regions, they kind of average out, and you still have a pretty good direction that works pretty well for those 100 images. I think we would have to go really deeper into the equations to see if the discontinuity in the derivative of the ReLU could potentially lead to convergence problems. I don't think so, but well, we would have to look at the equations really to see if the risk exists. In practical terms, I've never seen it. It converges. Other question? That was a nice mathematical question. Thank you. Yes?
Are they working on being able to train these models with smaller amounts of data? So I think it seems like the amount of data that you need is maybe gigabytes and terabytes of data in some cases. Is there any TensorFlow or research for how to train on less data?
Yes, there is. Most of the time, you need lots of data. But let's take one example where you can use less. It's for people who are in the previous version, it's this example here. This is a very big neural network that we use for image recognition. Oh, and the question was, sorry, I didn't repeat it, can we devise strategies for training the neural networks on less data? So usually, no, you need lots of data. But here, there is a strategy. So this is a 40-layer network for recognizing images. Like here, a wheel, and out comes the fact that it's a car wheel. This has been trained on millions and millions of images. So it's quite good. It's what we use in Google Photos and so on. Now imagine what you need is not car wheels, not the Eiffel Tower, not the Cathedral of Antwerp. You need to recognize flowers. And yeah, it doesn't do such a good job on flowers. So what you can do is actually take this fully trained network with all of the weights and biases already trained and simply chop off the last couple of layers. And you will use this as a fixed encoding function for your images. The idea here is that all of these are basically convolutional layers. So all of these have evolved into some kind of shape recognizers, and most of those shapes are generic. So you will still use them. You just use you don't retrain all of these layers, you just use them as a fixed encoding function. Give it an image, it gives you a vector of You choose the number of values, 100, 10,000 values, to represent this image, and then you train a small neural network, maybe just 2, 3, 4, 5 fully connected layers, to recognize from those values your categories, which are types of flowers, for instance. And there, well, you are training not all of those parameters, you're training just a couple of parameters in a couple of layers, so it's a more difficult CPU-wise, and you need less images to be successful there. This is a very useful technique for retraining a neural network. So that's one approach. There is not a generic approach, but case by case, there have been approaches. Last question, maybe? Yes?
Can you also generate larger data sets by creating more images yourself by making
Yes. Yes, definitely. That is also an approach because mostly what the network needs is noise plus information, and to be able to pick up the noise from the information, yes, that is a very good approach. If you know what the information is, you put it on a noisy background, and boom, you have 10 images out of one real example. That's completely applicable and useful. The question was, can you generate test data? And there are much more, even more clever ways of using a neural network to create your test data. Those are adversarial generative networks. It's quite fun, but I won't go into that. All right, thank you very much. I'm staying here for 5 more minutes, so if you want to ask more questions, please feel free to do so. Thank you.